In this video, we're going to discuss a really cool way of solving a linear system in two variables that involves the process of exponentiating a matrix. So let's go back to a simple differential equation of the form dy dt equals ay. This is simple exponential growth or decay. We know that this has y equals e to the at as a solution. In effect, the general solution is given by y of t equals c e to the at, where c is an arbitrary constant. Now, a linear system can always be written in the form dy dt equals a times y, and we're going to assume that A is a 2 by 2 matrix, so in which case we can view this as a two-dimensional version of this single variable equation. So think about dy dt is corresponding to dy dt. Of course, y is a vector valued function, and the A here is a 2 by 2 matrix, and the A here is a constant. Well, of course, any constant can be thought of as a 1 by 1 matrix, so we see a direct analog between these two equations. Since we can solve dy dt equals ay using an exponential function, can we somehow do the same with dy dt equals ay, the system? So that's a question we're going to look at in the next few minutes. More precisely, if a solution to the single variable equation is y equals e to the at, can we somehow say that the solution to the system is y equals e to the at? But A is a matrix, so what does it mean to exponentiate a matrix? We define the quantity e to the at as the matrix exponential. At a first glance, it may not seem to make sense, but we're going to use Taylor series to show that indeed it does, and this can be thought of as the solution to the system. So just recall for a moment that the Taylor series for the exponential function about the origin is the Maclaurin series e to the x equals the sum from n equals 0 to infinity x to the n over n factorial. So why don't we just substitute our matrix in? Using the expansion, we define the matrix, the exponential matrix e to the at, as an infinite series involving the matrix at raised to powers. Now, since scalars and matrices commute under multiplication, we can write this as the sum from n equals 0 to infinity a to the n t to the n over n factorial. I've simply taken this and rewritten at quantity to the n as a to the n t to the n. Now the right-hand side of this equation is the sum of 2 by 2 matrices. So e to the at, however we derive it, is going to have to be a 2 by 2 matrix. If C is a vector of constants, then if we take e to the at and multiply it by c, it's going to be a 2 by 1 vector, whose entries depend upon t. Now, provided this series converges in a meaningful way, and provided we can differentiate each term separately, meaning we can take the derivative of the whole thing by taking the derivative of each term separately, we obtain the following. So the derivative of e to the at times c. Now remember, this is a 2 by 1 vector that depends upon t. I've substituted in what e to the at is. And now provided you'll permit differentiating the series by differentiating term by term, we would have n t to the n minus 1 over n factorial. Our c remains out here. Now, of course, this n and this n factorial, this n and the n in n factorial cancel, so we're left with the following. Now the series starts at 1. I can relabel the terms here so that n minus 1 equals m. So the bottom would be m factorial. This would be t to the m. And we'd have the following. Now notice how I can rewrite a to the m plus 1 as a to the m times a, and I can factor in a out of this. But this quantity inside is merely the same as the matrix exponential e to the at. So what we've shown is that if we take the derivative of e to the at, and provided we can do all of this, we get a e to the at times c again. So that means that this has to be a solution to the system. So how do we know that the series converges in the first place? Let's focus on a simple case first, where D is a diagonal matrix, having entries lambda 1 and lambda 2 on its diagonal. So e to the dt, we would just substitute dt into our power series expansion for the matrix exponential. So this would be, if n is 0, we'd have the 2 by 2 identity matrix plus dt quantity squared, so on and so forth, which I can write in this way. The identity matrix, here's d times t, here's d times t squared, and here's d times t to the third. The nice thing about a diagonal matrix is that it's really easy to raise it to a power. So if, for example, I take dt and square it, I just get lambda 1 t squared, lambda 2 t squared, and then the 1/2 can be brought into the matrix this way. So this expansion can be written this way. Now let's add together all these matrices. Oopsie, I gave the answer away. So if I add the top left entries, I would get 1 plus lambda 1t plus lambda 1t quantity squared over 2, and so on and so forth. If I enter the bottom right entries, I would have 1 plus that, plus that, plus that, which we see right there. If I look at the top right entries, I'd have 0 plus 0 plus 0, and so on. And the bottom left entries, I'd have 0 plus 0 plus 0, and so on and so forth. Take a look at this right here. That's simply the exponential function evaluated at lambda 1t, and the same thing is true here. What we're doing is we're using the usual Taylor series for the exponential about the origin. So e to the d power is simply e to the lambda 1t, e to the lambda 2t along the diagonal. So it's fairly simple to raise a diagonal matrix, exponentiate it, so to speak. But what if we have a matrix A in general? Let's assume that A is a special type of matrix, meaning it's diagonalizable. We can write it as A equals PD P inverse. D is a diagonal matrix having the eigenvalues of A as its entries, and P is the matrix whose columns are the corresponding eigenvectors. Okay, now when can we diagonalize a matrix? Well, not all of the time, but if the eigenvalues of A are distinct, it's a fact that the eigenvectors of P have to be linearly independent, so P would be an invertible matrix by the invertible matrix theorem. Now, the nice thing about diagonalization is that it allows us to compute powers quite easily. A squared would be PDP inverse times PDP inverse, using the associative property together with the fact that P inverse times P is the identity matrix. We get the fact that A squared is just P times D squared times P inverse. Similarly, A to the third would be P times D to the third times P inverse. In general, A to the n is P d to the n P inverse for any non-negative integer n. And the nice thing about a diagonal matrix, again, is the fact that it's easy to raise to a power. So let's take our power series, e to the at, substitute in at. Now this is the same as if n is 0, we get the identity matrix, plus at over 1 factorial, plus at quantity squared over 2 factorial, and so on and so forth. Now, again, at is at times at, so on and so forth. Using the fact that matrices and scalars commute, this could be written as a squared t squared. This could be expressed as a to the third, t to the third, and so on and so forth. Now what we're going to do is we're going to replace a. Everywhere we see an A, we're going to replace it with the diagonalization PDP inverse. And we're going to replace the identity with PDP inverse as well. So you'll see now, A to the third, for example, is P, D to the third, P inverse, so on and so forth. Again, scalars and matrices commute. So I could replace P inverse T by T P inverse. I can replace P inverse T squared by T squared P inverse. And so what we have is the following. Notice how P is a left factor of each term here, and P inverse is a right factor of each term here. So we can factor them out, and we get the following. So we have the identity matrix plus dt plus dt, d squared t squared with that 1/2 there, so on and so forth. We can rewrite this way because, again, scalars and matrices commute. And this is just the exponential series for the matrix dt, which we've already shown is e to the lambda 1t, e to the lambda 2t along the diagonal, so p times p inverse. So what does this mean ultimately? If we want to exponentiate at, we simply use the diagonalization. We take our eigenvalues, e to the lambda 1t, and we take our eigenvalue lambda 1, and we look at e to the lambda 1t here. You take our eigenvalue e to the lambda 2t here. We left multiply the result by p, and we right multiply the result by p inverse. So let's take a look at an example. Let's suppose A is the following matrix, minus 7, minus 2, 4, negative 1. It's fairly easy to show that the eigenvalues are negative 5 and negative 1, and the corresponding eigenvectors are given by negative 1, 1, and negative 1, 2. So that means the matrix P would be formed as minus 1, 1, negative 1, 2, and it's fairly easy to check that this is the matrix P inverse. So e to the at, I write down P, I write down P inverse, e to the minus 5t, e to the minus 3t, and if you expand, simplify as much as possible, you get the following. So the top left entry would be that, the top right entry would be that, and so on and so forth. So that's the matrix exponential. It's really pretty easy when you think about it. So how can we use this to solve a system? And I seem to have lost a page. Okay, here we go. Let's solve the initial problem, dy dt equals ay, where a is the matrix we just had. And we're going to use the initial condition 2, 1. Okay, we know that a general solution to the system, we showed that before, is e to the at times the vector c, which is made up of constants c1 and c2. Now recall that e to the at, we know how to compute now. That's a 2 by 2 matrix. And c is just a vector, a 2 by 1 vector. So this actually is a 2 by 1 vector. Now if we substitute 0 in for t, e to the at becomes just the identity matrix. If t is 0, we have just basically the 0 matrix up here. So we get e to the 0 matrix, which is the identity matrix. So if we substitute 0 in for t, this becomes the identity matrix. This becomes our initial condition, 2, 1. So the vector c is, in fact, equal to our initial condition, 2, 1. So if we take y of t and right multiply it by the vector c, here's e to the at from our previous page, multiply that by 2, 1, we get the following solution. 5 e to the negative 5t minus 3 e to the minus 3t minus 5 e to the minus 5t plus 6 e to the minus 3t. So that's our solution. If we were to break this down into components, little x and little y, this is little x and this is little y, of course we could actually check that this is a solution. Now just a remark, let's suppose the A has complex eigenvalues, lambda equals A plus or minus BI. We know in that case the solution will have to involve sines and cosines. In this case, we can write e to the dt as e to the A plus BI times t, and I'm going to put the eigenvalue with negative real part down here, say, negative imaginary part, I'm sorry. Using Euler's formula, this would be e to the at times cosine bt, that should be bt. This would be e to the at times cosine bt minus the sine of bt. I'm using the fact that the sine is an odd function. So the sine of minus bt would be minus the sine of bt. So again, I'm using Euler's formula to rewrite this in terms of sines and cosines. Now the matrix P, if A has complex eigenvalues, the matrix P will be comprised of complex eigenvectors corresponding to the complex eigenvalues. However, if we take the product e to the at, we will actually get a real valued function. So even though e to the dt involves complex valued functions, and even though p and p inverse involve complex quantities, the entire result will simplify to be a real valued function.